You know, in geometry, trying to prove two triangles are identical, well, it can be a real grind. But what if I told you there were a few powerful shortcuts, tricks that could save you a ton of time and effort? Well, today, we're going to uncover the secrets to proving triangle congruence like an absolute pro.
So picture this. You've got two triangles sitting in front of you. They look identical, but in math, looks like just doesn't cut it, right? You have to prove they're congruent, that they're perfect clones of each other. So how on earth do you do that without measuring every single side and angle?
Exactly. I mean, measuring everything just feels so clumsy, so inefficient. There has to be a shortcut, right? A smarter, faster way to get to the truth. And thankfully, there is. We're basically on the hunt for the geometric equivalent of a secret passage.
All right, so this brings us right to the heart of it, the triangle shortcut problem.
Okay, so the traditional way, the brute force method, it's just exhausting. To prove congruence, you'd have to check that all three corresponding sides are the same length and that all three corresponding angles are the same measure. That's what, 6 different checks for every single pair of triangles? Come on, nobody has time for that.
So what's the secret? What lets us just bypass all that tedious work? Well, it's this really beautiful and powerful property that makes triangles totally unique among all polygons. And it's called triangle rigidity.
Yeah, the entire key lies in this property called triangle rigidity. This is the fundamental principle, the bedrock idea that makes all the shortcuts we're looking for possible. It's the reason we can do any of this.
So what is it exactly? Well, to put it simply, once you decide on a triangle's 3 side lengths, its shape is totally locked in. The angles can't change, it can only form one and only one specific triangle. Seriously, it's like a unique superpower that only triangles have. Think about it like this. If you build a square with 4 sticks hinged at the corners, you can easily squish it and wobble it into a diamond shape, right? It's floppy. But if you do the same thing with just 3 sticks to make a triangle, you literally can't change its shape without breaking it. Those sides lock the angles into place. It's strong, it's stable, it's rigid. And this amazing principle of rigidity gives us our very first and maybe simplest major shortcut. Let's talk about SSS. Okay, so the side-side-side postulate, or SSS, is just as simple as it sounds. If you can show that the 3 corresponding sides of 2 triangles have the exact same length, you know, the 4 centimeter side matches the 4 centimeter side, the 5 matches the 5, and so on, then that's it. You're done. The triangles have to be congruent. And here's the magic part. You don't even have to look at the angles. If those 3 side lengths match up, that property of rigidity we talked about guarantees that the angles have been forced into place, and they're going to match up too. It's an absolutely incredible time saver.
All right, so that's one shortcut down. Super useful. But what if you don't know all 3 sides? Well, let's move on to our next powerful tool. This one is called SAS.
So just imagine for a second, you know 2 sides of one triangle match 2 sides of another. Is that enough? Not quite. See, you could swing those 2 sides around at different angles and create a whole bunch of different triangles. We need one more crucial piece of the puzzle to lock it all down. And that missing piece, it's called the included angle. And this term is absolutely critical. The included angle is the one that's literally sandwiched between the 2 sides you know about. So if you have 2 sides that meet at a corner, the included angle is the one right there where they meet. And this brings us to the side angle side postulate, or SAS. It's just what it sounds like. If you can prove that 2 sides and that all-important included angle of one triangle are congruent to the same parts on another triangle, then congratulations, you've done it. The triangles are congruent. That specific combo, side, angle, side, is enough to lock the entire shape into place. But, and this is a really crucial warning, the order is everything. It absolutely has to be side, then the angle that's between them, and then the next side. If that angle is floating around somewhere else and not sandwiched between the 2 sides, this rule, SAS, it just doesn't work, so watch out for that. So, SSS and SAS, these are really neat tricks for your geometry class, for sure. But why does any of this actually matter in the real world? Well, as it turns out, these ideas are literally everywhere you look. Just take a look at this. This support structure for a tower, it's built from triangles. Now, the engineers know that certain sides are the same length, and they also know that the angles right there in the center are what we call vertical angles, so they have to be equal. So what do we have? We have a side, then an angle, then another side. That's side, angle, side. The SAS rule guarantees those two triangles are perfect clones, which is exactly what ensures the tower is stable, strong, and perfectly balanced.
And honestly, once you know what to look for, you'll start seeing this everywhere. The trusses holding up a bridge, the long arm of a construction crane, even the frame of a bicycle or the rafters in a roof, they all use the incredible inherent strength of triangles. They all rely on rigidity to literally hold our world together.
So, let's do a quick recap. What are the key takeaways? First, the big idea. Triangles are rigid. Their side lengths lock in their shape. And this awesome property gives us two shortcuts. First, SSS. 3 matching sides means you've got identical triangles. And second, SAS. 2 matching sides plus the angle between them also proves they're perfect clones.
So, this really leaves us with a final thought. These geometric principles, they aren't just abstract rules you find in a textbook. They are the invisible architecture that gives strength and stability to the entire world all around us. So now that you know their secret, where are you going to see these powerful triangles holding your world together?